Hi, welcome everyone. So we'll do a whole week of various topics that are centered around graphs. You'll see. So every day will be a slightly different topic, and every day we have a lot, okay? So there are 4 sessions, each 1 hour and 15 minutes. All sessions are interactive, so there will be a little bit of lecture, a little bit of exercise, Mathematica, so it's sort of woven in. So all 4 sessions are sort of equal in the way it's structured, okay? So hopefully it'll go okay. And if there are any questions, please stop me immediately. This is really, I'd really like you to understand everything. So don't feel shy, just ask questions, lots of questions. Okay, good.
We thought maybe not all of you are familiar with Mathematica. So we'll start with a very quick introduction. As Rekha mentioned, she will we have already shared a Mathematica demo file with you, which she has prepared. I just want you to get just the basic feel of the environment. The more you practice, the more you will get used to it. So Mathematica is a very powerful tool for symbolic computation and computer algebra. So I'll just give you a quick pointers of how things are done. So you can do basic numerical calculation. So it works as a calculator does. So it does all the things that a calculator can do. So whenever you see a cell, so this where I have highlighted is called a cell, okay? And you can evaluate any cell by pressing Shift Enter. Enter will not do the job. So if I just press Enter, you see it just go to the next line, okay? So you have to press Shift Enter to evaluate it, and then you see it says input 1 and output 1, right? So it has an input cell and an output cell. So you can add numbers, you can raise numbers to powers, and you can do arbitrarily large powers, as you can see, 3 to the 100, but you can also do 3 to the 1000. You know, these are exact calculations. There are no approximations here, but you can also approximate. So if I do n of that number, I get, you know, like in calculator language. So it's approximately 10 to the 477, you know, things like that. Pi is a special symbol. I mean, pi stands for the number pi, and you can approximate it to as many digits as you like. So here 200. I won't do everything, but here, okay, so let me show you how, because matrices are important for this course. So this is how you would type a matrix. So can you see, or is it too small? Should I increase? I can increase the font size. Yeah, thanks. Is this better? Okay, so you see, I wrote, so Mathematica uses curly braces for lists and lists of lists and so on. Actually, everything is lists in Mathematica. And so, if I just have a list, I would put curly brackets within single curly bracket. But now I have a matrix, which is a list of lists for Mathematica. So then I write it in this way, okay? And then I can look at it in matrix form. Okay, so this is how it looks like. You can see what it's doing. I'll share this with you. And now once you have this matrix, you can take its inverse. So instead of doing inverse of this, I'll just do inverse of m, because I have assigned m to that. Sorry. Okay, so this is the inverse matrix, and I can evaluate it in matrix form. So I can pass commands in this way. So using double slash. So this is the inverse of this numerical matrix. I can get the eigenvalues of this matrix. This is also going to be important. So here they are. And this symbol stands for the square root of -1. So it's a bold I. Okay, so this is like basic numerical mathematics, like things that an advanced calculator can do. but Mathematica can do symbolic calculation. So it can treat variables as variables. It understands that so it knows what 1 plus x cubed means. So you can expand it, and it knows that it's 1 plus 3x plus 3x squared plus 6. Okay. You can also factor. You can factor the previous expression. So Mathematica has quite advanced algorithms for factoring polynomials. So here, for example, this complicated polynomial in 2 variables x and y. If you expand it, you get this mess, but it also knows how to factor. Okay. So now here in this, I am treating this as a matrix of 4 symbolic variables a, b, c, d. So Mathematica doesn't know what they are. They could be real, they could be complex, but it can understand or it can evaluate these things symbolically. So it can compute the inverse of the matrix in the way that you learn in school, right? So it knows how to do it. So you don't have to specify pure numbers. It can be variables. Okay, we don't want to do much of calculus. Equation solving, do you need? Yeah, okay. So let me just quickly show you one example. So if you have a quadratic equation, for example, so x squared plus 2ax plus 1, a we don't know what it is, right? A is some arbitrary thing, but still Mathematica can solve it. So when you ask Mathematica to solve an equation, you have to put double equal to. So double equal to is it's not assigning. Otherwise, if you say this equal to 0, it will treat this as equal to 0. But we want to solve for x which satisfies this condition. So it's a conditional expression, just like greater than or less than. And I'm saying that we are solving this polynomial for x, not for a, right? So Mathematica will formally say this. So it's not assuming anything about whether this thing is positive or the discriminant is positive or anything. Okay? I mean, there are many more examples. You can, for example, find simultaneous roots of equations. So you want to solve for sin x being x minus y and simultaneously cos y being x plus y. So here you're trying to find a root of this system starting, and you give an initial value. So you say start off your algorithm with x equal to 1 and y equal to 0, and it converges and it gives you some answer. Okay? So things like that. So Mathematica can do many things. For one last example I'll give you is this linear solve. So you can solve a system Ax equal to b. So this first thing is your matrix A, and the second thing is your b. So it can solve it and it'll give you this. Okay, always shift enter is evaluate. Okay, alright. So with this small crash course on Mathematica, I hand it over to Rekha.
So I'm going to start from the beginning, like what is a graph? We'll establish the notation. Maybe some of you know some of these things already, but just hang in there so that hopefully we all have the same notation language, okay? So this whole course is going to be about graphs. So a graph for us will be, I'll denote it with the symbol G, and it consists of 2 parts. It has a vertex set and an edge set, okay? So this piece over here, these are the vertices. And typically, I'm going to assume that the vertex set is just 1, 2, 3 up to n, okay? So we're going to label it like that. Occasionally, we might call it V1, V2, and so on. And in combinatorics language, this is usually written like this, okay? So the set 1, 2, 3 up to n is just square bracket n, okay? So sometimes I will write that. So those are the vertices, and then this set over here, these are the edges of the graph, and this will be some collection of pairs. So maybe there'll be some ij's, and this is some subset, maybe not all ij's, but this is some subset of all the 2-element subsets of 1 through n, okay? So that symbol with when I put square bracket n choose 2 means you're taking every 2 elements from the set 1, 2, 3 up to n, okay? So it's a binomial coefficient, but it has a set inside. Good, so it may not be everything, so this is typically not equal, but just some collection, okay? So that's what it is. So let's do an example right away. So I want to do the Peterson graph, which is a very classic graph that has lots of amazing properties. So let's draw that, and then we'll look at it in Mathematica. So example. So our first example is the Peterson graph. Okay, so in the Peterson graph, you have a pentagon, and then you have inside it another pentagon. Okay, the outside ring is connected like a cycle, like this. And let's say I number this 1, 2, 3, 4, 5. And the inside vertices are 6, 7, 8, 9, and 10. But the inside is also a pentagon, but it's connected like a star, okay? So in the inside, we would start here, go to 9, go to 6, go to 8, go to 10, go to 7. That's the inside ring. That's also a cycle. But then you connect all these corners like that, okay? So that is the Peterson graph. So in this graph, of course, the vertex set is the set 1 through 10. So this is the vertex set. And the edge set is all the edges that you see here, right? So some of the edges are like 1, 2 is an edge, 2, 3 is an edge, but 1, 4 is not an edge. Good? So just to be short, I might often write the edges like this, 1, 2, okay? So this really means 1, 2, but sometimes we just write it like this if there's no confusion. So 1, 2 is an edge, 2, 3 is an edge, and then so on and on. There are 15 edges. So altogether, 15 edges, correct. So there are 15 edges to this graph, okay? All right, so this is a first example of a graph, and this is an example of a graph that is simple, meaning that there are no loops at the vertices, okay? It also doesn't have any double edges, so there are no multiple edges. So that's what simple means. It's connected, which means you can travel from any vertex to any other vertex. So we will always assume our graphs are simple and connected. And it's undirected, okay? So there are no arrows. And it is unweighted, okay? So there are no weights on the edges. So later, like on Thursday or Friday, we will look at graphs that have weights on it. And it's kind of important to study them as well. But for now, we will assume that it has all these properties, okay? So all of our graphs are going to be simple. They're going to be undirected. They're going to be, what else? What else did we say? Connected, correct, and unweighted. At least for now, they're going to have all of these properties, okay? Let me introduce some more notation. So for the Peterson graph, if you look at how many edges touch a vertex, it's always 3. Everywhere it's 3, okay? So the number of edges that touch a vertex is called the degree of the vertex. And if the degree is the same everywhere, then we call this a regular graph, okay? So in this example, the degree of a vertex, so remember a vertex is just a number, so I'm going to write degree of I, okay? This is equal to 3 for all I inside our vertex set, which is the set 1 through 10. And if you have this situation, if you have this for all I, then we say that this is a 3 regular graph. So everything I teach in this week apply to non-regular graphs, but the theory is a lot more easy if you assume regularity, okay? So we will just assume regularity for this week, more or less. You can experiment with non-regular graphs in Mathematica by yourself. Good? Okay, so these are some of the very basic notation. So let's take a look at the Peterson graph and some of the things that Mathematica can do. Sorry, I'm trying this whole system of getting the chalk out of my hands, but we'll see if this works. So this is the Mathematica file that you have. Can you see this? Should we make the font bigger? So can you pull up this notebook? It probably doesn't show any of the pictures. Do you see it? Can I see somebody's? Can I see yours? Okay, you got that. Okay. Can everybody see at least, you may not see the picture, but you should see the command on top. Can you see that? If you hit Shift-Enter on the first line, you'll see this picture, but I just want to make sure everybody has it.
So for him, it just says graph data Peterson graph. Just type Peterson graph on the next line. Where's your cursor?
Sorry, what does it say?
Your cursor is there.
It says this one.
Yeah,
Just
exactly.
type Peterson graph. No, don't click anything. Just type. Type PET.
Can I see what you have?
Yeah.
Oh, you deal with it?
Shift enter.
Well, do you have the notebook?
Controller.
I'm not connected. This is the notebook.
No, the notebook.
From the overleaf that we sent yesterday.
Yeah.
I'm not connected.
Oh, yeah.
Not connected.
Okay, so maybe connect up, or maybe just share with her for just now. If it's not working, just share with your partner so that we can move on, and then in the break you can. Does everybody have a partner that can?
It says Peterson graph.
Can I see it?
Just says graph data Peterson graph.
This was the first line, right?
Yeah.
And somehow it didn't work for you.
Let me check on that.
Where's your shift and where's your enter? Nothing happens?
No, there's no Wi-Fi.
Oh yeah, you need Wi-Fi. I don't think it'll work without it. Do you guys have EduRoam? Oh, they use this?
I lost.
Okay, so we do need that. I may just go on until we figure out these technical difficulties, okay? Because there's a lot going on. So let's keep going, and don't worry. You can just look at this or look at your neighbor, okay? All right, so if everything worked perfectly, you should have just downloaded a file that had no pictures, just the commands, okay? If you go to the very top, there is up here, there is this cell called evaluation. If you click on evaluation and you go here to evaluate notebook, if you click on that, the entire notebook will evaluate. Okay, so you can see all of the pictures at one shot, or you can do one by one. You can press Shift Enter on each line. Do you see that? Do you have that piece? Okay, if you don't have it, don't worry. But you can just press Shift Enter, okay? This is a Mac, so I don't know if it's different. Okay, is everybody good for now? All right, so this is the Peterson graph, the one that we just saw. Good? Okay, and the way the command goes is that graph data is a database of graphs that Mathematica has. And if you put, colon and type in the name, like if you start Peter, it'll complete it for you, okay? And it has tons and tons of graphs in it, so it'll give you lots of options that you can complete to. In this case, it is the Peterson graph. So we get this graph over here. So the next command is, we can ask Mathematica. So if you look at this version, there are no numbers on the vertices, okay? Okay. So we can figure out the technicalities in a bit, all right? Do we want to wait for this to work, Arvind?
No, please.
I'll just keep going? All right, we'll figure out the technicalities in the break, okay? So don't worry right now. Right, so right now we don't know how the vertices are numbered inside Mathematica. It has some numbering, okay? It has some number from 1 through 10. So the next command is asking it's asking for the name of the vertices. So if I say graph, and then Peterson graph is the name of the graph, and I write vertex labels, arrow, and then name, then you get the names on the vertices. Okay, so you don't have to memorize this. It's already there. You can just play with it. So just learn by example, I guess. Okay, so now you see that it's numbered this way, which is a little bit different from the way I numbered the graph, but it's fine. Okay, this is how Mathematica would number it. Okay, then some other things you can ask for is you can ask for the vertex list, and then it'll tell you the vertex list. You can ask for the edge list, gives you the edge list, okay? And then there are more graphs we can play with. For example, there is the house graph, which is this graph that looks like a house, like this. And then you can do the same things. You can ask for the names of its vertices, and so on. Okay, so there's a few more graphs in the list that you can do by yourself. So let me just move on from here. Is this okay? Are you anxious to get this working, or?
So that won't work unless the internet is connected.
I guess so. Yeah.
So can you try this new password? I think that's why it did not work for you also. So it worked? Okay, so this password seems to work.
Okay.
Yes.
So maybe take a minute to make it work and try 1 or 2 more graphs. So it's working for you.
Anybody having trouble downloading the
file?
file?
You good?
Yeah, I made, but the internet what is supplied is not working.
No, it is working. You have typed, you made a typo. Show me what you have typed.
Okay, how's it going here? Is it working? Your internet is not working? No. Okay. Can you check again the password? Because it's working for some people. Okay, you're all having trouble with it. You're okay. You're okay. I don't know where this got caught. Okay, yours is working. So now click on the codes. Just click on it. Click on the arrow maybe. Go to day 1. Click on the arrow. And you need to download that file. Okay? Okay, how are you guys doing? It's working? Okay, good. Great. You're good? What's the issue? Do you guys have it too?
I'm not able to connect Wi-Fi, but is this working? The diagram is not coming.
If you don't have internet, it won't work. Mathematica needs internet. Yeah. So maybe let's get the internet going first. You're okay, right? Okay. How about you guys? Is it working for you all?
No.
Is it the internet? Is it?
Internet, I have my hotspot, but it is still not working.
Did you download the file?
The internet is a problem.
I think you need to first go download the file. So if you go to the overleaf and then download the file, I can help you if you go there. You're good?
Yes.
Okay. You're okay? You're okay? Okay. You? Excellent.
Okay, this
Yeah.
project which I got the mail yesterday.
Yeah. So go to codes, click on the arrow, click on the arrow. Go to day 1, click on the arrow. Yeah. Yeah, and then download that file.
This one.
Yeah. So download it. It won't preview it, but you can download it.
See, I gave this thing, it gave me this graph, this is fine, but now how do I give
So you need to first download the whole notebook. Do you have the overleaf account?
Overleaf,
So let's go to the one that Arvind sent you yesterday.
overleaf account is here.
No, so not this. So Arvind sent you an overleaf folder. Did you get it by email?
That is also there.
Okay, so you need to open that account, that folder.
Projects. Yeah, this is, I got something here.
Okay, so just click on it if.
Yeah, this is,
Yeah, so click on it. Go to day 1, yeah, and then download that file. And then it'll come up in Mathematica. Yes?
This is done, but the features in graph is not showing.
What does it say? Correspond to the syntax. Okay, no idea why that's complaining. Did you do Shift Enter there? Okay. For you too, so same? And your internet is working? It needs internet, otherwise it won't work. Okay, so we may have to figure this out in the break. I don't know, that's more complicated than I understand. Is it working for you? For none of you? Okay. What could it be? And you all have internet?
For me, it's working.
For you, it's working. Okay. And for you guys? Okay, can you just look at each other's for a moment, and then we will figure it out in the break. Okay? Okay, I think it's working for most people. So if it's not working, just share, please, and then in the break, we'll figure it out. Arvind, you there?
Yeah.
You're good? Okay, so we'll just keep going?
Yeah, that's good.
Okay, so there are a few more graphs you can try. Please share. If you can't do it, you don't see it. Let's see, maybe even go to 125. Okay, so I have another graph here. And for this one, I asked for its vertex degree. And it tells you the degree of all the vertices. So this graph is not regular. as you see. Different vertices have different degrees. So this is telling you all the different vertex degrees. Okay? Then there are further commands like this command over here on the top called 5 vertex graphs. That's asking graph data to give you all the graphs on 5 vertices. Okay? It's not all the graphs in the world. It's all the graphs that's inside Mathematica on 5 vertices. Okay? So then it gives you a list, and then this loop over here is allowing you to draw each of these graphs. So if you if you do the next command, this is like a for loop. It's a table. It's taking graph data, 5 vertices, that list, and then it's asking you to draw every one of them. Okay? So that gives you the picture of all of these graphs. And so you can try these later. There's another graph here. Again, you can ask for various things about these graphs. And you can call your own graphs. You can put in graph data, colon, whatever, and then it'll give you all this data. Okay? So this is just to let you know that Mathematica has thousands of graphs stored inside it, so we can just use it, and then it'll also give you all kinds of information about these graphs. Okay? Okay, so if you don't mind, we'll just keep going and not worry about the technical things because there's a lot today, okay? So let's try to get through some more stuff. Everybody good? Okay. All right, so this is the first thing. So the whole day today is about linear algebra. So the topic for today is we're going to look at the linear algebra of graphs. Okay? All right, so to do linear algebra, we need matrices. So the first thing we'll look at is we're going to look at several different matrices that are associated to graphs. Good? So the first one is, I want to look at, let's look at matrices of G. There are many, many, many matrices. For us, we're going to focus on a few ones. So the D, I'm going to call the degree matrix. Degree matrix of G. And what this is just a diagonal matrix with, on the diagonal you see the degrees of all of the vertices, okay? So this is basically a diagonal matrix, and in the diagonal you see the degree of vertex 1 all the way up to the degree of vertex n. Good? So that's what it is. We'll do an example in a second. And the next, so for example, in the Peterson graph, so if we take this example, then the degree matrix, is just 3 times the identity, right? Because every vertex is degree 3, so you get a diagonal matrix, and on the diagonal you see 3, 3, 3, 3, 3 all the way down, okay? So this one is pretty easy. So this is going to be 3 times the identity of size 10. Right? So this is always a matrix that lives in, so D always lives in R n by n. Okay, so it's a real matrix of size n by n. So that's the degree matrix. And then we also need, the first type of big matrix we'll study is the adjacency matrix. Okay, so we're going to focus a little bit on this matrix, and I'm going to call this A. This is also n by n matrix, okay? And the definition of this matrix is like this. In the ij entry, we're going to put a 1 if ij is an edge, and we're going to put a 0 otherwise, okay? So it's going to record the edges of the graph. In the ij entry, you put a 1 if it is, if ij is an edge, otherwise you put a 0. So let's do an example. So I want to do the house graph because it's small. So here is the house graph. And I'm going to number it like this, 1, 3, 5, 4, 2, okay? You can number it whichever way you want, but once you fix the numbering, you should just work with that, okay? So up to permutation, it doesn't matter. You can change the labels whichever way, it doesn't matter. So that's the house graph that we saw earlier in Mathematica, right? It's this graph. Oh, it's not going to work with one finger. So there it is. So let's write down the adjacency matrix for this graph. Okay. So first of all, this is a graph, it's a matrix of size 5 by 5, right? There are 5 vertices, so it should be something of size 5 by 5. So its rows and columns are indexed by the vertices, and this also by the vertices. I hope this erases. Yeah, it does. Okay. All right. So in the diagonal, what happens? So if you look at the II entry, what should we see? Just 0, right? Because we're not allowing loops. We're not allowing I to connect back to I. So this is always a matrix with diagonal 0. So I get 0, 0, 0, 0. Okay? So that's one property of it, that it always has the 0 diagonal. And then we start putting the edges. So for example, let's focus on this first row. This corresponds to vertex 1. So I look at what it's connected to, right? So 1 is not connected to 2, so we put a 0 here. 1 is connected to 3, so you put a 1 here. 1 is connected to 5, so you put a 1 here. It's also connected to 4. Okay? So this is the first row of the matrix. It's just recording all the edges that's connected to 1, right? And then what happens in the first column? Do you see immediately what should happen? Should be the same, right? Because so this first column is also, once you've done that, this is easy. So we just go ahead and do this, okay? And then you can finish this. So for example, let's do maybe one more row, maybe the second row. So the second row is 2 is connected to 5 and 4. So it's connected to 5 and 4, but not to 3. And then again, it's symmetric. So this will be 0, 1, and 1, okay? So this is the adjacency matrix of the graph. It's telling you where all the edges are, and its information is equivalent to knowing the graph. Do you agree? If I just gave you this matrix, you could construct the graph. And if you have the graph, you can construct the matrix, okay? So it's a way to represent a graph. And to do any kind of linear algebra, we represent it using matrices instead of with a picture or with a data structure that actually captures the picture. Good? So this is the adjacency matrix. So let's look at some of its properties. What are some other properties? We already saw it's symmetric. Do you agree? Anything else that strikes you? Like if you've studied matrices and linear algebra, what other property might jump out at you? Well, okay, all eigenvalues are what?
Real.
All eigenvalues are real, exactly, and that's coming from symmetric? Okay, so this implies that all the eigenvalues are real. So in particular, it means that you can order them, right? There are no complex eigenvalues, so I can order the eigenvalues. So I'm going to order these eigenvalues in a particular way. So let's call the first one mu1, the biggest one. And this is less or equal to mu2, is less or equal to how many eigenvalues? N, right? It's an n by n matrix, so it has n eigenvalues, maybe with multiplicity, but it has n eigenvalues, and we're going to always fix this ordering, okay? Great. So it's symmetric, so it can do this. What about the eigenvectors, since we are doing this already? What kind of eigenvectors will this have? Symmetric matrix. It has a full set of orthogonal eigenvalues, which means we can also normalize it, so it has a full set of orthonormal eigenvalues. Eigenvectors, correct. And the matrix is diagonalizable. Do you agree? So all of these things come from being symmetric. So let's call the eigenvectors phi1, phi2 up to phi(n). So these are eigenvectors. And this we can assume are orthonormal. So it has norm 1 and they are mutually orthogonal. Okay? So eigenvectors will always denote them as phi1. And the matrix is also diagonalizable. So I can write this matrix as a sum, this is the matrix of eigenvectors, times this mu matrix. So let me just write it like this, like a big matrix. And then this is inverse or transpose. What should we put here? Yeah, because it's orthonormal, the inverse is the same as the transpose. Okay, so we can do this. So this U consists of the eigenvectors arranged in the columns. This mu is diagonal with, let's say, mu1 up to mu(n), and then U transpose is the transpose of U. Okay, so it's diagonalizable. So all of those things come from being symmetric. So that's wonderful. Do you see 1? What happens if I multiply this matrix with the all ones? Okay, so let's take this matrix and let's multiply it on the right with the vector 1, 1, 1, 1, 1, 1, 1. This is the all ones vector, okay? What happens? What comes on what is the answer? Do you see? Yeah, so over here, which we don't have space, but you should see the degree of the various vertices, right? So can you see this color in the back? Okay. So all we're doing is we're taking the dot product of each row with the all ones. So it's just counting how many edges are adjacent to 1, how many are adjacent to 2, and so on, right? So in the first one here, we'll get a 3, and that 3 is telling me that vertex 1 is adjacent to 3 other vertices. Then here I get a 2, and here I get whatever. You can read it off from the graph as well, right? So you get this, but whatever this is the degree sequence. This is the degree sequence of the graph G, okay? So if I multiply A with 1, I get exactly that. Good. What happens if the graph is regular? So if G, this is not regular, okay? But if G is, say, D-regular, so that means that all the vertices have degree D, then what happens when we do A times the all ones? Yeah, if you do this, then everywhere you're going to see D, 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 D. So this is the same thing as D times 1, okay? And that tells us one eigenvalue and eigenvector of this matrix, right? So this tells you that D is an eigenvalue with eigenvector 1, 1, 1, 1, 1. Good? So this gives us one eigen, so this is important that it's D-regular, otherwise this doesn't work. This is not an eigenvector, right? Because I multiplied with 1, 1, 1 and got some complicated thing here, I can't take anything out. So this tells me that D along with 1 is an eigenpair. Okay? So eigenpair means it's an eigenvalue along with its eigenvector. Good? So D1 is an eigenpair. Okay? So one of the things I'm going to ask you to think about, or maybe you know this already, is to argue that if you have a D-regular graph, then its largest eigenvalue mu1 is D. It can't have a bigger eigenvalue, okay? So maybe you have a proof of it, but hopefully by some of the things you're seeing today, you'll see an easy way to see that. That's the largest eigenvalue, okay? So if you're D-regular, then this is going to be the largest eigenvalue of the graph.
Mu1.
Sorry?
Mu1.
Mu1, yeah, it's going to be mu1, exactly. But let's wait to prove this. You'll see a very easy proof after we do something else. Good? So right now, we have one eigenvalue and eigenvector for this. And you see the eigenvalue is positive. Even if the graph is not regular, the eigenvalue is positive. This requires a proof. Okay, but let's go to that piece first. Okay, so this is maybe what you see in Mathematica if you go a little bit more. So let's look at this for a second. Okay, so the next command up here in the top, I'm calling A Peterson graph, that's a name, to be the adjacency matrix of the Peterson graph. Okay, so Mathematica has a command called adjacency matrix. And if you type in the name of the graph in the box, it'll output the matrix for you. And as Arvind showed you before, what it outputs is like some string. And I put a semicolon after the command in the top line. So it suppresses the output. You can't see the output that Mathematica actually gives you. But if you don't put the semicolon, you'll see a string. Okay? But then if you say matrix form of that, you see it in the form of a matrix. Good? So sometimes we are happy with just a string, but sometimes we actually want to see the matrix. And you see it has all the properties, zeros on the diagonal, symmetric, all that kind of stuff. We can ask for its eigenvalues. So I ask for the eigenvalues of A Peterson graph. That's the name of the adjacency matrix, and you see this. Okay? So it has negative eigenvalues, it has positive eigenvalues, but 3 is the largest eigenvalue. Right? That's the degree of the graph. Good? And then we can ask for eigenvectors. It gives me a bunch of vectors. And they're pegged to the eigenvalues. So it means that this first eigenvector, 1, 1, 1, 1, 1, goes with this first eigenvalue here. Okay? So they're ordered by the way the eigenvalues are pushed out. So notice this is not in ascending or descending order. What order is this? Sorry?
In magnitude.
Yeah, exactly. It's an absolute value, okay? Descending in absolute value. And for adjacency matrix, that's usually how it comes out. And you'll see later that it has a physical meaning, that there is a reason why the absolute value is the correct way to order the eigenvalues, okay? So there's actually a frequency, like a physics meaning to this. So that's why it outputs it like that. These are the eigenvectors. And you can play with more examples, but let me just finish the demo. So one thing you might get into trouble when you're working with these eigenvectors, you have to remember what Mathematica gives you is not orthogonal, okay? It's of course orthogonal between eigenspaces, but inside one fat eigenspace, it might just give you some basis, okay? So between eigenspaces, it has to be orthogonal, right? Because eigenspaces of symmetric matrices are orthogonal. So that's okay. But you see, this matrix has a lot of multiplicity, right? Like 1, 1, 1 is done so many times. So there are 2 fat eigenspaces and one align eigenspace, which is the 1, 1, 1 eigenspace, right? So within those eigenspaces, it gives you some basis, not orthogonal, definitely not orthonormal, okay? And you can check that because what I did here is I took that list. So remember, this is secretly a matrix. It's a list, but it's also a matrix. So I took that thing. It's called Eigenvex A Peterson graph. Okay, I took it and I multiplied it with its transpose. Okay, and I got this thing back. This is not the identity, right? You can immediately see without even looking at the matrix form. This is not the identity. Okay, so it's not. But you can ask it to orthogonalize the vectors. So you can take the vectors Eigenvex A Peterson graph, you can orthogonalize it, then you get something that looks orthonormal, right? It's got all these square roots at the bottom, which are the norms of the vectors. So we do that. And then it's like messy, but it's correct, okay? And this happens like you're deep into some code and you realize it's all garbage and you have no idea where this garbage came from. And you see, oh, that's because the eigenvectors it gave me in the beginning were not orthogonal or orthonormal, okay? So you have to be careful. So this is the orthonormal version. And now I called it U, that is the name of this matrix. And now if I do U dot transpose U, I do get the identity. You see this is the identity, right? It's all right? Okay, so that's just a caution. Okay, and then there are a few more examples over here. When do we stop, Arvind? 10:45, right? Okay. Okay, so if your thing is working, you can type a couple more examples in and you can see some more examples. That's the house graph. This is the A house graph. This command in line 300 is the adjacency matrix of the house graph. We just did it on the board, right? Its eigenvalues are not nice numbers, so it's some floating point representation. That's where you put the n in the front, okay? If you didn't put the n in the front, so for example, let's take away the n. Okay, so if I took away the n and I did this, you get this. Okay? So you get like it's written as the roots of certain polynomials. That's how it's written. So this is very difficult to understand. So that's why we put the n in the front, which is the numerical expressions for these eigenvalues, and then you see something that's more human readable. Good? And then, okay, this one may be a little bit harder to see how the eigenvalues are sitting. So I asked for a list line plot. That means all of these points are the eigenvalues, these breaks. And then it's just drawing a line between them so that you can actually see them. If they're just isolated dots, sometimes we can't see them on the screen. Good? So that's how that one goes. And there's the all ones and so on. Okay, so I'll leave you to play with this later. Okay, so that's the Laplacian. Okay, good. So let's leave that there. So you can play with the other examples, okay? So you can just copy paste all this code. That's, I think, the easiest way to learn, or put it in ChatGPT, tell you how to do it, right? That's how I write code in Mathematica, because I can't remember the syntax. I say, how do you do this? Blah, 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 blah. The code will come back. You just copy it in, okay? So that's, anyway, this is code. Okay, so now let me go to another property of this adjacency matrix. What else is good about this adjacency matrix? Symmetric was good.
I have something bad about it.
Bad about it, okay.
I want to know if a vertex, I don't know, if you take a unconnected graph, the vertex which is not having any edges to any other thing, then it causes problem. I don't know.
What will happen? It's a good question. What's your name?
Sudhakar.
Sudhakar is asking if you have a disconnected graph, it'll be bad news. What's the bad news? What happens to the adjacency matrix if we had a disconnected graph? It'll block diagonalize. It'll block, right? So all the things that are connected together in one piece will have its own adjacency matrix.
Even if you have one vertex, it's gone.
If you have one vertex, there are no edges, you'll just get a 0 in that block.
Yeah.
That's fine. It's fine, okay? So it'll be a bunch of adjacency matrices that are blocked, right? And that will come up later sometime today, but normally we're going to assume the graph is connected, okay? Thanks. Okay, another property. Let's look for one more property before 10:45.
Sum of eigenvalues is 0.
Yeah, sure. Some may be 0. But I'm looking for a more global property of the matrix. Like you said, symmetric. That was great. We got a lot out of it. Okay. What else? Like when you look at that matrix, what other matrix property might jump out at you? Is it positive semi-definite? It is not. Yes or no? Okay. Okay. Correct. It cannot be PSD, definitely not PSD, so let's look for something else. But it has some very interesting property, right? It's filled with zeros and ones. It's non-negative, okay? It's non-negative, and non-negative matrices have a big theory in linear algebra. There's the whole Perron-Frobenius theory for non-negative matrices, okay? So let's use that fact, and let's write down some more things about this thing, this matrix. Okay. So it's non-negative, and what does that buy you? Does anybody know some of the properties of eigenvalues and eigenvectors that come out of non-negativity of the matrix? Slightly louder, please. So if I write like that, that means the entries are all non-negative. That's what it means, okay? So A is a non-negative matrix, and because of that, there's something called the Perron-Frobenius theorem about non-negative matrices. It's actually Frobenius because Perron is for positive matrices where there are no zeros. Ours is not a positive matrix, it's a non-negative matrix, okay? So the theory is a little weaker, but it's a 19th century theorem from the Frobenius and Perron. Well, I don't know where Perron is from. Frobenius is definitely from 1800s, right? It's a 19th century theorem. And this theorem, Frobenius, tells you, so we'll see, let me call it, so people call this Perron-Frobenius, but I'm separating it because Perron is really for positive matrices, okay? Like Google PageRank is a Perron theorem, the way that it shows you the Google pages when you Google for something. That is a positive, that's a Markov matrix, it's positive. Okay, so let's do this. So this tells you that if A is non-negative, then this implies that A has a dominant eigenvalue. So it has a very important eigenvalue that we'll call dominant. And we'll call this lambda A. Actually, let's call it mu A, since all the eigenvalues are mu's. And the key thing about this eigenvalue is that, one, this mu A is non-negative, okay? So it always has a non-negative eigenvalue. And its eigenvector, which let's call it phi A, Okay, so phi is my notation for eigenvector, mu is the notation for eigenvalue right now. So the eigenvector that goes with this eigenvalue is also non-negative. This is part of the theorem, okay? Good, and then the second piece is that for every other eigenvalue of A, let's call it just mu, it must be that the absolute value of mu is less than this dominant one. Okay? So what this is saying is that it has a top eigenvalue which is non-negative, and it comes with a non-negative eigenvector. We're going to immediately prove that this is actually a positive eigenvector. And then every other eigenvalue has absolute value less or equal to mu A. Okay? So that means if you draw a picture, here's the origin, mu A is, we're going to show that it's actually positive. Okay? The theorem only tells you that it's greater equal to 0, so it could be 0. But we're going to prove it's positive. And then somewhere here there is minus mu A. Okay? And what the second piece is telling you is that all of the other eigenvalues are here, inside this range. Okay? So if you have any other eigenvalue mu, it must lie between mu A and minus mu A. Okay? So there's a bound on the absolute value of any other eigenvalue. Good? This is Frobenius. Good? Okay, so this came out from being non-negative. Okay. So if you have, so can we look back at a graph? So if it was a regular graph, we already agreed everything is fine, right? This was an eigenvalue, definitely positive, that's the degree of the graph, okay? This was its eigenvector. So at least part one is okay. There is some eigenvalue that's non-negative with a non-negative eigenvector, but you see it's actually positive with a positive eigenvector. We're going to show that soon. But if you don't have a regular graph, this is not an eigenpair, right? So what happens? Can we go back and look at the house graph? So let's look at, was here, right? Yeah, this is the house graph. And in the house graph, the eigenvalues were these numbers. So 0 is an eigenvalue, and then there are some other numbers, okay? So the dominant one is the first one, the 2.48. And then do you see that all the others are in absolute value less than that one, right? They're all smaller. But let's look at its eigenvectors. So this is not an eigenvector, because if I multiply with this, I just got the degree sequence back, right? That's not an eigenvector. But we can ask for the eigenvectors. So maybe I have it here. That's the path graph. Okay, I don't have it here, but we can ask for it. So for example, we go here, okay. All right, no, I don't want that. Okay, so we can ask for its eigenvectors or, okay, A house graph. So maybe it's just not running.
Because can you evaluate that again?
The house graph?
No, the all ones.
Oh, that one, yeah, okay.
Even the later one.
Yeah, okay. Yeah, okay, fine. And then if we ask for eigenvectors, we saw the eigenvalues, but if I ask for the eigenvectors, so you see it'll just complete like that, so you can just do that, and then it also knows the names of things you gave it. I maybe have to evaluate everything. A house graph, oh yeah. It's very difficult to do this in real time. Okay, so we got this thing back, which is a mess, so we put the n in the front. Okay, so this comes back, okay? These are the eigenvectors. So you see the first eigenvector, this one, goes with the dominant eigenvalue, okay, this first one. And notice that it's completely positive. Every entry is positive, but it's not the all ones, okay? So let's argue that that is actually going to happen, that it's going to be a positive eigenvector, and the eigenvalue is something positive, that's also there, but it's not the all ones, okay? So this theorem works no matter whether you have a regular graph or a non-regular graph. Okay, so to finish this session today, let's do a proof. Yeah? Question? No, not for this version. I think for irreducible, you'll get probably something more. Yeah. There are many of these theorems. So there's Perron, which is a particular way. I don't think you need, or maybe this is already irreducible. You have to check. Sorry?
For the connected graph, it is also reducible.
It is
Which is always
irreducible. Excellent. Okay, then we're good. All right, good. So then, yes. I'm just claiming this for the adjacency matrix. Okay? So let me erase this bit, and we're going to argue that okay, just out of curiosity, is all this very familiar to everyone? Some people who knows all this already? Just show of hands, please. Okay, not everyone. Okay, so I'm still going to do it, okay, because many of these things are going to come back later for other purposes. So we're going to do this. Okay, so let's actually argue. So here's a fact that I will not argue. Maybe you can ask the people who know the theory later why this is true. So one fact is that mu1 is positive. In fact, mu1 is bounded below by the average degree of the graph, okay? That means you count up all the degrees, you add all the degrees and divide by the number of vertices, that's the average degree, so that's something positive. So it's bounded below by that, okay? And it's bounded above by the max degree. So this implies that mu1 is positive. So I'm not going to prove this, okay? So you can think about this or ask your friends, and they will tell you. And then by Frobenius, we also know, so this is some new fact, but from Frobenius, we also know that mu1 is going to be greater equal to minus mu(n). Do you agree? Because mu1 is greater than the absolute value of mu(n). Mu(n) is the last eigenvalue, which means it's greater equal to minus mu(n). Good? So we also know that. And we know from Frobenius that phi1 is non-negative. So we know both of these from Frobenius. Okay, so Frobenius only told us that it's non-negative. So now I'm going to argue that it's actually positive. So let's do this exercise. So let's argue that phi1 is actually positive. Okay, that's the claim. Phi1 is a positive eigenvector. Okay, so let's do the proof. So what do we have to show? So Frobenius already told us it's non-negative, right? So all I have to argue is that there are no zeros anywhere, right? So suppose there's a zero. Let's do a contradiction proof, okay? So let's suppose that there is some vertex, let's call it A, where the phi1 value is 0. Okay, so we always think of eigenvectors as functions on the graph. So think of the numbers you see in the eigenvector as numbers that are sitting on the vertices. Think of it as a function, okay? So it's typical to write this for the value of phi1 at the vertex A, okay? So suppose this happens. So there is some vertex A where the value of the eigenvector is 0. Okay? Now this is a connected graph. That means this A is connected to other vertices. Maybe there are some other stuff like this going on. Okay, that's the rest of the graph. Okay? Now it could be that near this A, it's also 0 for a while. Maybe this is also 0. Maybe this is also 0. I don't know, something like that. But because it's connected, there's some edge where it has to transition from a 0 to something positive. Do you agree? Because the whole vector is not 0. Eigenvectors are never 0, 0, 0, 0, right? They're non-zero vectors. So there must be some edge, maybe this edge, where it transitions to some, so let's call this vertex B in white. This is B, this is C, and here I have some positive number. So this is some positive value, okay? So there must be some edge where there's a transition from 0 to a plus. Agree with that?
Maybe erase the AC edge because people might think.
Oh yeah, that's right. Okay, so let's put it here. Let's put it here and do this. So this is B, this is C. Okay, so there exists, so this means there exists some edge BC. There exists an edge BC such that phi of B is 0, but phi1 of C is positive. Good? This has to happen. Everybody okay with this? Okay, so now let's use what we know about the adjacency matrix and the fact that this is an eigenvector and so on, okay? So first of all, what happens if I do, so phi1 is, remember, the eigenvector of mu1, okay? That's important. So what happens if I do mu1 times phi1 of B? Okay. Mu1 is positive by the fact phi1 of B is 0. This is 0. This is something positive. So this definitely is 0. Is that okay? That's definitely 0. Okay, but on the other hand, let's think about what this is, right? So here's the adjacency matrix. And then I just multiplied it with phi1, which is a vector. And then on the other side, I should get mu1 times phi1 again. Right? This is how the eigenvalue, eigenvector thing looks. So we're focusing on the row that has B in it. Okay? So if I focus on the row that has B in it, so maybe this is the row. Okay? So this is B. These are really sharp colors. Sorry, these are my colors. Okay, let's focus on that row, right? So we just calculated, so in here you see this entry over here is phi1 of B, and we just calculated mu1 times that, and that's equal to 0, okay? But on the other side, what happens if you multiply this, so this entry came from, these two multiplied together came from this row multiplying this vector, right? So let's do that calculation. Let's multiply the B row of the adjacency matrix with phi1. That's exactly mu1 phi1b, right, on the other side. So we know the right-hand side value is 0. But this is the same thing as if I took A times phi1, okay, that's the left-hand side, and then just looked at the bth part of it, the bth entry in it, right? So it's that. But what is this without the B? If I do A times phi1, what are we summing up? So in here there are some, there are some ones, and those are the only things that are active, and that's exactly where the edges are that connect B to something, right? So on this side, this piece over here, this is going to be the sum of A times everything connected to B, let's call it BZ. Okay, so these are so BZ is an edge. So I only look at the things that are connected to B. So from here, everything connected to B. So I have to sum that up. Sorry, yeah, so A times BZ is all ones actually. So what do we actually get? So if I do this, I will be summing up. I will pick up the values of phi1, okay? Yeah, so we'll pick up the values of phi1 at Z, or Z, okay, where the Z is connected to the B. Do you agree? This is what's happening on the other side. Okay, great. What's one of those Zs? C, little c, right? Little c is one of those Zs. So what can you say about this sum? How does it compare to phi1 of little c? Greater than, exactly. So this is greater than that, right? But this is positive by our assumption, right? We assume that phi1 of C is positive. So we get a contradiction. We have 0 is strictly greater than 0. Do you agree? So this tells you that there cannot be any place where phi1b was 0. If there was, then there's something somewhere along in the graph, there is a place where it transitions from 0 to positive. Okay, so we pick up that edge, we pick up that B, and we do this calculation. We look at mu1 phi1b, this is 0, so this is 0, okay? But this is the same thing as this row of the B vertex multiplied with the phi1. That's this calculation, which is the same as this calculation. But little c is one of the Zs, so that's greater than phi1c, which is positive. Questions? I have some people shaking their head. Everybody okay? Please ask. Yes. Sorry. How did we get what?
So how did we get the existence of C?
Oh, how do we get the existence of C? Good question. So the graph is connected, okay? I started, so we're assuming that somewhere there's a 0, so A, okay? And then it could be, so everything else has to be either all 0 or somewhere positive, right? It can't be all 0 because it's an eigenvector. Eigenvectors are always non-zero vectors, right? Can't be all 0. That means you walk along from A, and somewhere you have to pass to positive. That's the existence. Good question. What's your name? Saraswati. Okay, very good question. Is this okay? Everybody okay? Okay, that's the existence of the C. And then once you have the existence, this is linear algebra. We just use this fact, right? So we're using the fact that A phi 1 is mu 1 phi 1. That's this equation. And then I am evaluating the bth entry on the right and left. Okay, in the right, you get 0. The left gives you something physical, right? We're adding up the edges that are connected to B. We're adding up the entries of the phi 1 vector on those edges. C happens to be in there. It's messing things up. So, contradiction. Good? Okay, so this has a strictly positive. So what we've concluded is that phi 1 is strictly positive. This is the thing, okay? What did we actually use? We have 1 minute. Can you make a stronger statement? So I just proved to you that phi 1, which goes with mu 1, is strictly positive. Can you strengthen it a little bit? So this was we didn't really use this, right? We just used the fact that this was 0, so this is 0, and then this all happened, and so on. So what happens if we just had a non-negative eigenvector? Doesn't matter what eigenvalue, just a non-negative phi. Can you argue it has to be then positive? So I have a non-negative phi. Comes with some eigenvalue, maybe mu 1, maybe mu 3, maybe mu 10. Who cares, okay? It's a non-negative eigenvector. Can you run the same argument and conclude it has to actually be positive? If it happens to be non-negative, it has to be positive. You can't suddenly have 0 somewhere, right? That's all we actually used. So the statement we actually proved is that any non-negative eigenvector is actually positive. So there's nothing sitting on the hyperplanes in the orthen, right? If you look at the Rn, there's nothing sitting on the coordinate hyperplanes. It's either entirely in the positive part or it has some negative value in it. Okay, so it's a pretty powerful property of an eigenvector. So this is all I have to say about the adjacency matrix for now, but we'll go on to other matrices.